instrumentation and control. The first question I think I'd like to answer is, why measure? Because it seems to be an afterthought for most people. They always add the measurement systems last, and if at all. And I think it's one of the most important things, and it should always be designed in from the ground up. And here's why. If you look at the current state of the art with software-defined networking, it's really about static provisioning. And with static provisioning, you really don't know what your demand is. And so you guess. And then you, as a prudent engineer, you build in safety factors. So you say, well, I'll double it. And then I think, well, maybe I'll double it again, because nobody's going to really fire me for over-provisioning. But if we run out of capacity, I'll be in trouble. And who will know that there's too much capacity anyway, because we don't have any measurements. And so you end up with all this expensive capacity that's not used. And then if you're successful, demand for your service increases. And at some point, you run out of capacity. And it's a complete surprise, because you're not monitoring. And everybody panics and buys a bunch of new equipment. And then maybe demand for that service declines. And then you end up with all this stranded, unused capacity. And one of the problems with poor management of capacity is it's sort of an insidious problem. It only exists because the measurement system that would have eliminated it isn't there. And without the measurements, you don't actually know how big the problem is. And so you're completely unaware of the costs associated with wasted and misplaced resources. And so what really we want to do is have resource demand and capacity closely matched. And as demand chain increases, capacity is added, and as demand decreases, capacity is removed. And then, in a cloud environment, this is real money. If you're in EC2, if you can release a VM, you don't pay for it. And if it's your own data center, you can flex that capacity to a different application. So, for instance, running Hadoop at night with spare capacity that you would otherwise be using during the day. And so my background is control engineering, and anytime you look at something like that when you want to adapt, it's a control system. And this is the way we look at control systems. You have the system that you're trying to manage, in this case, a network of switches and the servers that are attached to it. And then you have a measurement system that's going to measure how that system is performing. And you're going to compare the performance with some desired objective. So suppose you want to run your system at 80% utilization, your desired output is to run at 80%, and you're measuring what capacity you're actually using, and then your controller is dynamically adding and removing resources as needed. And then there's a critical sort of concept that comes with feedback control, and that's the idea of controllability and observability. And there's a lot of math behind it, and you don't really need to pay too much attention to that. The basic concept is pretty simple. And the idea is that to create a stable feedback control system, you need to be able to influence all the important states in the system. And that's controllability. And you also need to be able to monitor all the important states in the system. And that's the observability part. And there's kind of dual properties. Each state in the system needs to be both observable and controllable. And to sort of make this clearer what this is like, that picture is kind of hard to read. What it is Tule fog in the Central Valley. That's Highway 5. And it's trying to illustrate how important visibility is to control, in this case of your car. And to illustrate the idea of feedback control here, the states associated with your car are its location, speed, direction. Those are the sort of parameters that describe its motion. Observability is the observation that if you can't see the road, it's hard to stay on the road. And you can't keep to the speed limit if you don't have a speedometer. So you need feedback in order to drive well. In this case, you're the controller. And you also need controllability. So if you have no ability to steer the car, you can't stay on the road. If you don't have a gas pedal and a brake, you can't maintain your speed. So really, it's showing you that the three key elements here is an understanding of what the key states are, the ability to observe those states, and the ability to manipulate and control those states. Another really important thing is the effect of delay on stability. And basically this top timeline unwraps the control loop that we were looking at. And so there's some kind of disturbance happening. In this case, I'm kind of looking at a denial of service attack. And so the disturbance is the attack is launched against your data center. And then there's some kind of measurement delay. It takes you a while to recognize, A, that you've been attacked, and B, to sort of characterize the attack, identify what resources have been targeted, who the attackers are. And then you need to, there's a planning delay. You have to figure out what to do. Is it a really large attack? Should I null route the traffic? Is it smaller? Is it an application sort of logic attack? Should I run it through some scrubbing service? So lots of different things you could do based on your characterization of the attack. And so that's your planning delay as you think what the most appropriate action is. And then the next thing is your configuration delay. So you have to go out there and, if it's manual, you log into a switch and you change its configuration. Maybe you put in your null route. And then there's a response delay as that change takes effect. And so if you were changing a routing table entry, that route has to propagate through the internet. And then at some point you finally see the effect of your control and the denial of service attack disappears. And then it's a closed loop, so you're monitoring and you're seeing the effect that has actually taken place, and you keep going around this loop. And the important thing is that the time to traverse this loop has to be sort of proportional to the time constant of the thing you're trying to manage. If you're delayed in your response, then you risk actually making things a lot worse and destabilizing them. And so getting back to the car driving analogy, a way to sort of think about response time is how you drive if you're sort of tired, drunk, or distracted. If you're slightly distracted, you would tend to weave around, maybe drift out of your lane. If you're very slow in your reaction time, you leave the road, and that's the case of being unstable. So given that context, let's think about, talk about sFlow and why it's a really suitable measurement system for control. The first thing is that sFlow is an industry standard that's very widely supported. And this kind of ties into that observation about observability. That if I want to create a large span of control, everything that I want to control has to be observable. So if I want to, there's more than one vendor in most data centers, and so you would like every vendor to support a standard that gives you observability. And with OpenFlow, controllability. And so increasingly, these vendors are also implementing OpenFlow, which gives you the two things you need to build robust and interesting control systems. The other thing you want to do is, again, this is increasing the span of control. The network by itself isn't your whole system. There's all the servers that are making use of it, and then the applications that are hosted on top of those servers. And it's really the applications you want to control, and you want to deliver the service they need in order to operate correctly. And so you need instrumentation that extends into the servers, hypervisors, and application servers that are running in the data center. And that's where the Host sFlow project comes in. It's a set of open source projects that embed sFlow instrumentation in these different areas like Linux and XenServer and so on. And the Open vSwitch is a really critical component of that. It gives you visibility into the virtual networking. And actually, it's interesting, that's kind of the motivation behind moving sFlow into servers, is that as sFlow went into virtual switches, you can't really understand the performance of a virtual switch in isolation. If the server that's hosting it is thrashing, then the virtual switch performance is bad. And so you need the server statistics, and it's kind of like pulling a thread on a sweater. Pretty soon you've drawn everything into your web. This next slide, really, I don't expect anybody to read in detail. It's just making an observation that counters are a staple of network system and application performance management. In the networking case, a bunch of interface counters are maintained in hardware for each port on the switch. On servers, there are a number of key performance indicators maintained by the kernel. In applications, there are various counters as well. And the problem is that these counters don't do you a lot of good if they're stranded within each switch, server, and application. What you really need is an efficient way to export those counters and make them actionable. And that's really where sFlow comes in. It's a very simple push protocol. So every device that has something to say just sends those metrics out. Each of those blocks of counters on the previous slide is represented as a structure, which is a densely packed block of counters. It's extensible. You can add new structures. It's got a tag length value encoding. It uses XDR to serialize the data. And it uses a unicast UDP transport. So it's very simple, about as simple as you can get. And it also requires minimal configuration. You just need to say who to send all this data through to and how often. And push protocol is really important, particularly in sort of cloud environments where you have very dynamic systems where virtual machines are being added and moved, started, stopped. If you have polling systems, it's really hard to know who to poll. Whereas if you have instrumentation embedded in every resource that you deploy, as soon as that resource spools up, it starts sending metrics. It's immediately discovered and continuously monitored. And so you have continuous and full visibility, which again is critical to stable controls. So why are counters so popular? Well, they're incredibly useful because they collapse enormously complicated state space. So here's a trend showing the utilization on a 100 gigabit link. It's carrying about 14 million packets per second. Each data point on that chart, which is reporting at minute intervals, is nearly a billion packets summarized. And so that's a tremendously condensed version of what's going on that link. And so it gives you a very clear idea of how utilized that resource is. But it's not enough. Because when you see that a spike in the chart, what do you do next? That's not really an actionable metric. What you need to be able to do is then disaggregate that aggregated counter in terms of all the constituent parts that you threw away to make that number in order to find out what the root cause of any load is. And that's where the second part of sFlow comes in. And that's the random sampling. And sampling is incredibly lightweight. For roughly the cost of maintaining one more counter, you get full visibility into all that high cardinality data. So for instance, in a switch, you'd be randomly sampling packets. You count down to 0, you capture a packet header, you reset the counter, and you start over again. And so all the switch needs to do is maintain that one counter and send a copy of the packet to the management entity every time it resets. Sampling is incredibly easy to distribute. It doesn't require any synchronization. You can distribute it among sort of threads in a worker pool, ports on a switch, blades across a blade server. It really is very loosely coupled. And because it's stateless, the data is immediately sent out. It requires minimal resources. But with this data, you get to identify those high cardinality resources. So for instance, here we're looking at that same link again, and you can see that the traffic is being driven by 3 large UDP flows. And you can see what the addresses are, the ports are, you can see how much traffic is flowing in each of those. And it's doing that at 14 million records per second at wire speed. The other thing you want to do is, for scalability, is have all the agents be very loosely coupled. So with sFlow, the agents don't know about each other. They're acting completely autonomously. But the data model in the standard allows the receiver of the sFlow data to dynamically join this data together. So for instance, when you get sampled packet headers, the MAC addresses and layer 4 sockets are present in the packet header. And so when an sFlow agent on a host exports server metrics, what it also does is exports the server adapter MAC addresses. And that way, you can join the host's identity and performance with the traffic that's visible on the network, and link performance to packet paths and so on. And at the application layer, if you're running, say, HTTP sFlow running in a web server, what you're doing is you're sampling at layer 7, so it's HTTP transactions. You're getting URLs, response times, HTTP status codes. But what you also get is the TCP socket that request was received on. And if it's a proxy, you would get the upstream and downstream sockets. So you can link the global address space to the private address space in the server pools, and link performance problems between the front and back end. And all this data is dynamically joined at the collector and gives you this unified view of performance. And so really that's the goal here, is to make the entire data center observable, which is one of the prerequisites to making it controllable, and an essential element if you're going to develop adaptive software-defined data centers. And so really that's the goal here, is to have embedded monitoring in everything, operating all the time, so that it can drive control decisions. And by using a standard export, you sort of break the coupling between agents on all the different devices and the analysis tools that you use. So the same data can be fed to different open source and commercial tools, and you have consistency because you have standard measurements that everybody understands, and you are comparable between all the different tools. So moving on to software-defined networking. The exciting thing about OpenFlow is that it allows you to close the loop. It's the forward control path. And so this is a diagram representing what a closed loop controller looks like with the combination of sFlow and OpenFlow. And so what sFlow gives you are these very low latency stateless measurements in a central location. And then with your software-defined networking application, you're automating decisions. So instead of a human taking minutes or hours to solve a problem, you can act within milliseconds. And with your OpenFlow controller, you can provision changes in a similarly short time scale. And so you've dramatically transformed the agility of management of all of these resources. At this point, I'd like to look at sort of alternative strategies for monitoring. And really, sFlow, what this diagram shows you is what happens inside a switch doing both sFlow and OpenFlow, or IPFix, or any sort of flow-based measurement. With sFlow, there are two tasks we talked about. There's the switch will autonomously poll and export all the hardware counters that it's maintaining. And the other thing it's doing is randomly sampling packets and immediately forwarding them to a collector, and that's all it does. But if you look at flow analysis, there the analysis is actually being done on the device. And so there's a sort of deep pipeline of additional tasks that the switch has to perform. It has to be able to decode the packets and understand them. It has to populate a flow cache. And then it has to run algorithms to decide when to flush records. And then it sends them to a collector. And one of the problems with this is really the delay it introduces. Because if you think about it, that flow cache is state that's unknown to an external observer until it finally gets exported. And as we saw, delay destabilizes your controllers. And so this next slide really kind of does a side-by-side comparison of what that delay looks like to the receiver of the measurements. And vSwitch is a really nice test bed for this kind of thing because it can do both NetFlow and sFlow. And so I set up a simple sort of test bed where I have a real-time sFlow analyzer next to a real-time NetFlow analyzer, and run a large flow through the vSwitch. And you can see here that the blue line is when the flow starts. And you have an active timeout delay before the first flow is exported from OpenFlow, and that's the first spike that you see there in the green at the bottom. And then there's a second spike which is the second active timeout. And then there's a third spike, which is the end of the flow, and the final record comes out. Whereas with sFlow, you're getting a constant stream of samples, and so you're able to immediately detect and continuously monitor that large flow, which is the kind of control signal you want if you're going to do adaptive load balancing of large flows in the network. The delay and punctuated measurements that you get from flow-based monitoring really doesn't make developing stable controls easy. And as I said, OpenFlow has kind of the same architecture. You're building a flow cache on the device, and you're either getting the flows on exploration or by polling, which is similarly delayed. So really what sFlow adds is actionable visibility to an SDN stack. And here I mean by actionable that it's complete, that you're observing everything, and it's timely. If it was delayed, it's not very useful for control. You might use the data for other things, but for real-time control, you need rapid response in your measurement system. And so drilling down a little further, again, think of this as a control loop. You have the switches sending measurements up to your SDN stack, and then you have your sFlow analyzer, and then you have a northbound API providing RESTful access to those metrics. And then you have your application running it there, and then you have an OpenFlow controller, like Floodlight or something, with its RESTful API, and then it's deploying controls back down. And so you can then build dynamic feedback controllers using this architecture to do interesting things. And the two architectures are very similar between OpenFlow and sFlow. There's minimal stuff happening on the switch. You're basically configuring the protocol as to who the central analyzer or controller is. And so with OpenFlow, you set the controller, and with sFlow, same kind of thing. You just say who the analysis engine is going to be. And then you're done. Everything else happens at the central analyzer and software. So the use cases I'm going to be looking at are denial of service mitigation, load balancing of large flows in switch fabrics, optimizing virtual networks, and packet brokers. And these are only just a very small number of examples, because this is a really newly emerging area, and there are an enormous number of ways in which you can apply measurement that wouldn't otherwise address applications that wouldn't otherwise be possible with OpenFlow. And there are even more use cases if you broaden your horizons and say, well, it's not just the network. I'm actually interested in automating everything in the data center and coordinating the network with application workload placement and so on. And that opens up a whole range of other use cases. So for anybody who doesn't really know how DDoS attacks work, this is sort of a basic diagram of a denial of service attack. The attack is launched by sending a message out through a control network, and then it finally reaches a bunch of compromised hosts, which then send traffic to the designated target. And for a flood attack, they're trying to overwhelm the links as they get closer to the target. And so this is an example of actually using real-time sFlow data to mitigate that kind of denial of service attack. And there's a sort of before and after picture. This large data center regularly sees denial of service attacks sustaining 6 million packets per second, about 30 gigabits per second. And I've seen as many as 5 of these attacks within a 10-minute period. And without control, they will just go on for hours. And so with real-time detection with sFlow, you're able to figure out what address is being attacked. And in this case, because they're huge flood attacks, the only real response that they have is to use BGP to steer that traffic, and generally they'll not allow it and drop it. And so here you can see the kind of the fast response you can get. Within a couple of seconds, the attack has been detected, a couple seconds more, the BGP policy has been changed, and the response is so quick that actually the attack never fully evolves, because it takes some time for the controls to be deployed across the attack network. And if you can drop the route faster than the attackers can be mobilized, you can see that the attack peaked at around 1.5 million packets per second, about a quarter of what it would otherwise be. So that way the pipes are not getting saturated anymore, and really those attacks are now under control. And there's also another really interesting use case that was on packet pushers, and I'll put the URL up there. People can look at that as well if they're interested. And that one's a little more subtle. What they're doing is actually using sFlow to identify the individual attackers and mask them individually through scrubbers. So whereas this is sort of more of a sledgehammer, that was a little more of a scalpel. The other really interesting use case is load balancing ECMP or lag multipathing. What's interesting about this is the kind of load balancing that switches do is essentially hash-based. You look at various header fields, you compute a hash, and then you do a modulo the number of paths you have, and you pick a path. The problem with that is random is really not very good for load balancing. Even if you have a one-to-one subscription ratio, so you're not technically oversubscribed, you still end up with a bunch of collisions. And one way to kind of illustrate that is how many people kind of know the birthday paradox? It's the basic question is, how many people do you need to have in a room for there to be at least a 50-50 chance that two of them will have the same birthday? And you'd think that that would be pretty small, because there are 365 days in a year. 23 people is not many. As a utilization of the year, it's 6%. But it's a 50-50 chance that two people have the same birthday. And if you look at the number of people in this room, I had it pegged at 90, I think we're maybe at 80. It's a virtual certainty that two of us have, or at least two of us, have the same birthday. And that only represents 25% utilization of all the slots in the year. And so the probability of collisions in using hash-based load balancing is extremely high, actually. Surprisingly high. But fortunately, if you look at traffic studies, most of the bytes transferred on networks exist in a very small number of long duration flows. So the vast number of flows are very short, and they're load balanced easily using hashes. But most of the utilization is in these longer flows. And they tend to run in the range of durations of 10 seconds to and longer. And, if you're looking at storage associations like iSCSI or something, it'll be forever. And they dominate the bandwidth consumption in the network. And so those kind of timescales are really amenable to software-defined networking control. If you can jump in and steer a flow within 2 or 3 seconds, you've steered the vast majority of all the bytes on your network. And so you have immense control over the utilization of resources. And what's interesting is it doesn't apply just to ECMP, it applies to lags and lags. You could look at wireless or WAN traffic management as well. And it also, you can do really interesting things. You can do things like take longer paths than the short, if ECMP just takes equal cost paths, but there's a lot of residual capacity in paths that are longer than that. So it gives you the opportunity to mop up all the links in your network. And especially if you use measurement, you can now do things like Google has been doing with their WAN, is you can accurately mark traffic. And so if you can mark a lot of traffic that really isn't time critical, things like data replication, and make that less than best effort, then all your normal traffic doesn't see it at all. You can still be over-provisioned with respect to that, and then you mop up all the additional bandwidth in your network using this low priority. But again, that requires really good end-to-end coordination and marking, and that's where I think a really good use case for vSwitch is to do the marking, and then you do the steering and traffic engineering within the physical fabric. And there's actually an interesting draft that's been taken up by the IETF operations work group that's looking at just this problem of large flow load balancing in ECMP and lag environments. And so it'll be interesting to see how that evolves. The next example that I thought I would address is network virtualization. And since this is the network virtualization group, I thought it would be a good one to look at. And I particularly like this diagram because it's, I think it clearly shows all the elements. Basically, the current state of the art is to set up a bunch of tunnels that overlay virtual network traffic over the physical fabric using GRE and VGRE, VXLAN. And currently, the actual network topology is hidden from the orchestration tools. So, you know, the system that's managing the placement of virtual machines is completely unaware of the topology of the fabric that's carrying that traffic. And that causes some interesting problems. So if you see, you know, a nice virtual network at the top there, you know, firewall, load balancer, and a few virtual machines, as you map that down into the physical fabric, if the virtual machines are, if the orchestration system is unaware of the network topology, the virtual machines end up being essentially randomly placed with respect to the physical topologies. And so you end up with this real sort of spaghetti of traffic flows. And it makes it look as if there's a completely flat traffic matrix. That, you know, basically everybody talks to everybody and there's no pattern. And so if you're given that kind of traffic matrix as a network architect, your only solution really is to build a flat network. And that's a very expensive thing to do. I mean, it takes a lot of cost, power, space. It's kind of an inflexible architecture because it has to be highly symmetric. And so, you know, if you want to add one more port, you might have to add a whole new pod or something. You can't just throw things together. So there's sort of a mix of sort of operational flexibility on the physical infrastructure. Network virtualization is great as a service to present to upper layers because that abstraction is really useful. But I think in order to realize that abstraction, a good orchestration system will do a good job of managing the physical resources on which that abstraction depends. And so that's really what this next slide is looking at, is saying, okay, if I have really good analytics, you know, this traffic really isn't random. And if you think of a multi-tenant environment, your policy is to isolate tenants. That's the whole point. And so the traffic matrix is in fact incredibly sparse. And so really what this is showing you is that if you were to sort all the hosts by tenant, you would see that it's sort of a diagonal matrix with no traffic between tenants, because that's by design. And in fact, because it's so sparse, there's a lot of residual capacity there that you could use more effectively. And by structuring the traffic so that it is hierarchical on the physical network, you can do a lot better job of doing the dynamic provisioning that we were talking about before. And you can do a better job of isolating performance between tenants. And if you scramble all the traffic together, then there is no performance isolation. One tenant overloading a link will affect other tenants on that link. Whereas if you're doing a better job of partitioning tenants, there's less interaction, and it makes the job of controlling performance and deliver quality of service easier. And also, you can then get sort of really creative about the way you provision things. I mean, if you were trying to host that set of tenants there, then really your largest tenant is the only sort of like constraining thing in that environment. And so if you can use things like optical circuit switching, you can essentially wire up high connectivity for that large tenant, but not waste a lot of links connecting all that white space around the tenants. And the other thing is that this is sort of fractal. I mean, if you look at any one of those tenants, their traffic is incredibly sparse as well. And this is looking at what traffic looks like in a Hadoop cluster. And so a lot of tenants in a hosted environment will be running Hadoop maybe at night when they have idle resources. And it's very striking similarities. And the reason for this very strong diagonal in that traffic matrix is that Hadoop is topology aware. It's, it tries to localize bandwidth to racks wherever possible. And so what those little clusters of dots represent are exchanges between machines within the same rack. And what's interesting is if this tenant is now in a hosted environment, you've doubly hidden the topology from Hadoop. And so it's also scrambling all its traffic across the network when it could do a much better job of localizing traffic. And so finding ways to create feedback paths. So instead of just provisioning down, you're providing information about topology and utilization up the stack. Then a tenant, and Hadoop doesn't really want to know details of the physical switches and links. It just needs a logical name that says, okay, here's this hierarchical name, and if the names match, then you're close, and as you go up the name, you're further and further apart, and then it can do a job of localizing traffic, and you get, the fewer hops you use for a typical connection on the network, you're making better use of the physical resources, and you're getting better latency and better throughput for these kinds of jobs. So the fourth use case is an interesting one. This is actually one that Microsoft presented at the recent ONS conference, and it's their daemon distributed sort of tap system. And they have tens of thousands of tended ports that they have to monitor and be able to tap them and feed that data into various sort of security and analysis tools, like Wireshark. But this is way too much data for the tool to handle. So you need to be selective about what you tap. And so what they're doing is they're using sFlow to basically get a sense of what all that traffic is and decide what taps to open up. So when the switches are all blocking, you're still getting the sFlow data, and then you can say, okay, I'm seeing some weird traffic here, maybe I'll tap it, and then I'll run it through Wireshark and do a deep inspection of it. And there are a number of ways in which this gives you sort of advantages. You get visibility at traffic volumes that you couldn't possibly capture if you were looking at every packet. But you can also, if you're using OpenFlow to do the captures, it can only operate on the sort of 12 tuple fields in OpenFlow. Whereas sFlow can look at anything in the first 128 bytes of the packet. So you can do really interesting things, like say, okay, I'm interested in seeing behavior in my tunnels. If somebody's DDoSing one of my tenants, I'd be interested in that. And so you can use sFlow to do that, to look to see which tenant is being attacked, and then find the outer addresses for the tunnel that is transporting that traffic, and then trigger OpenFlow to tap the tunnel, and then you get full visibility into that data. But you couldn't do that with OpenFlow alone. You need visibility into those other fields. And tunneling is not just for network virtualization. Increasingly, most IPv6 transition strategies involve things like IPv6 over v4, and so you get really interesting problems for security where you want to be able to peer in the tunnels, but yet use tools that are not tunnel aware to do things like capture. So that's the sort of end of the sort of background part of the talk. I was wondering whether it's good to maybe break for some questions now, and then we'll move on to the tutorial, please, or to hold all of them to the end. Okay.
So does sFlow support sampling based on the flows?
No, it's complete. It has no concept of flow. It's just pure random packet count based sampling.
Can I configure it? So let's say I have 10 flows going through my switch. I have 10 network slices which make the traffic flow through a particular, say, OpenFlow switch. So can I do a sampling based on a particular flow?
No. And again, if you think back about the goal here of doing control, that if you're selective in your monitoring, you're by definition now unstable. Because you could have this stampede of things that is sucking up all your bandwidth and you're not seeing it anymore.
No, the thing is that when I do sampling, it might happen that I'm skipping some flows and I'm not getting any sample from those flows.
Yeah, but what you're getting is an unbiased view of consumption of resources.
So it's some kind of an overall thing which I have to make a judgment on.
Yes, but generally it's not much of a judgment call. You know, you're very insensitive to sampling rate. Now, I've seen a lot of people, you know, they basically set up the sampling rate once and they deploy the system and they never change it. And you could double the sampling rate or halve it and you wouldn't notice. And you can actually get surprisingly good data with very few samples. And we have one site that they're actually using a sampling rate of 1 in a million. And they're getting all the data they need.
Yeah, but at times when we virtualize a switch code,
yes,
right, at that point I may have a chance of missing some samples. If I want to do some analysis on a particular
well, that's the point, is you are missing most of it. That's why it scales. And if you want to see that detail, then OpenFlow in this kind of environment is a terrific way to tap it. So it's the combination, you know, sFlow gives you this really good overview, and then you can deploy other tools to, you know, to look at details.
Yeah.
So I sort of see it, analogy I used was, you know, if anybody does astronomy, you sort of have the spotter scope that gives you the wide angle view of the sky, and then it helps you point. If all you could look at is through the main telescope, it'd be really hard to find anything. And so that's really what sFlow is there. It's a blanket monitoring of everything, so that you can manage resources and you never miss anything.
Peter, could you talk for a minute? I was interested to see that it does have applicability at monitoring your application level performance.
Yes.
And are there some? Can you talk about that for a minute? Its effectiveness.
Sure.
Is it used?
Yes, it's
widely at that.
But it's pretty new, so it's kind of rolling out. But
okay.
At the application layer, some examples are, you know, like there's mod sFlow for Apache, and so what it does is it's a module, so it's running in the Apache web server itself, so it has zero overhead, and really what it's doing is it's just randomly sampling HTTP requests, and then you can get high value data like response time, the status code, the URL, the user agent. It's also maintaining.
You can locate clients out wherever you wanted to in the world.
Yeah.
Right.
And the idea with sFlow is that each entity has some natural state. So it's kind of an unnatural act for a layer 2 switch to report URLs. It's not what it does, you know. But for a web server to report URLs, they're right there.
Right.
It's doing no extra work to tell you the URL. And especially when you're doing random sampling, even if you're doing very high transaction rate services like Memcache, for instance, where you might be doing hundreds of thousands of requests per second. You're just doing it, again, it's very efficient because you're just taking a random sample of those requests. And then you're getting high value data like the key, whether it was a hit or a miss. And now I can find hotkeys in my enormous cache with maybe 1 billion entries in it, right, which would otherwise be an incredibly difficult thing to do, or missed keys. And so that's really high value data at the application level that's easily obtained. And you can do it operationally. So you run this continuously, it has no impact on the operational systems, but it gives you tremendous visibility. And for like load balancing devices like HA proxy or ADC boxes, it's really useful to be able to get both the front end and back end sockets that you get from sFlow. So you'll be able to see, what path do the requests take over my physical fabric. Am I seeing packet loss on those paths? What the discard rates? And so I can correlate across all the different layers. And if you're running a server, the Apache data by itself isn't sufficient. You'd also want to know whether the CPU is overutilized on the box that's running Apache, or whether it's swapping. And so all 3 layers are tied together.
Great.
How is this different from NetFlow?
Sure. With NetFlow, the sampling, you can configure sampling in NetFlow, but the analysis is then done on the switch. So it builds a flow cache. And that flow cache because it resides on the switch, is inaccessible to your controller. And so while the data is there, it's not actionable. It's only actionable when it hits your central controller. And then you can do really interesting things, like say, okay, I've got 100,000 ports on my network. Which one's overutilized? You know, no individual switch knows that. Which is the busiest port? You know. Yeah, but it's export on cache expiration, so it's later. And so it's that delay that causes problems if you're trying to use this data for real-time control.
That's not dynamic.
Yes, sFlow stateless. You know, the instant the packet is sampled, it's sent to the collector. So there is a flow cache, but the flow cache exists in the central software. And it's actually much more scalable to do it that way, because if you think about it, on a network, most links are idle and there are a few busy links. And different links become busy at different times. And so if you look at the memory utilization of all the flow caches across all the switches in the network, it's very poorly utilized. And yet there are some switches whose caches are overutilized. And so you drop measurements. Whereas if you pool memory centrally, you fully utilize the memory. You're not wasting memory on things that that stranded in the devices in the network. So you use far less memory to build a more complete cache centrally than you would if you had to use the really expensive memory that's in your CAMs and all your switches, which you'd much rather use for more OpenFlow entries anyway, rather than for measurement. Yes?
So I'm thinking in terms of like the physical switch position as a top of that. Does sFlow use a direct traffic visibility? Heading towards the connected servers, like who are the top loaded servers and top topper hosts in terms of packets per second or open connections or connections per second?
Yeah, I mean, the Toprax switch is actually a really interesting sort of intersection between, the server DevOps folks and the networking folks, because servers generally are very poor at monitoring their own I/O utilization, whereas the Toprax switch, it's the other end of the wire, and it's got a hardware sampler, and so it sees all the traffic going in and out of that host. And so when you combine sFlow data from the switches, from sFlow data from the servers. So the server sFlow is telling you CPU memory utilization, I/O ops and stuff, and then the switch is telling you, how many packets per second of iSCSI are going through to that server. And you put the two together, and you have a really complete picture of external I/O and internal behavior that accurately characterizes the performance of scale-out clusters. And it also helps you with troubleshooting because, if you think about the state space, if I have 100,000 servers and I see a problem with one server, which of the other 100,000 servers does it depend on? It's a hard problem. But if you're monitoring the network as well, you see what the dependency graph is. You see, okay, he's reliant on this guy for storage, on this guy for DNS, on this guy for WAN. And so you collapse that state space, and it becomes pretty trivial to diagnose most problems. Whereas if all you saw was the data on the servers themselves, it ends up being a harder problem to solve. Does that answer your question?
Yeah, it does. The follow-up question is that there are some of the use cases that you presented were quite interesting, specifically the software-defined analytics use case. So all that it requires is switch support of sFlow and OpenFlow, right, for these use cases to work.
Yeah, I mean, the analytics part is just sFlow, and then for the dynamic control, not all of them require OpenFlow. I mean, sometimes the response is a provisioning exercise. So for instance, if you want to use BGP to drop a route, that's going to be a configuration action. But for the fine-grained flow controls, yeah, then it's OpenFlow, and you put the two together and you can do these.
sFlow is a CPU-intensive operation, right?
No. I mean, on the switch, it's very little CPU because it's basically the hardware is doing the heavy lifting, It's, wire speed. You can have a switch with, hundreds of 100 gig ports, and you can run sFlow on all of them all the time at 100% capacity, and it works because it's in the ASIC.
Yeah, but when you talk about servers and switches, I understand, because the ASIC will have support for sampling, and then you can do it. On a server, if I were to run an sFlow agent, right? I know there's a multi-core thing, but will it scale in terms of running?
Well, on the server, there's two use cases. One is like a vSwitch, and so if it's you build it into the vSwitch, and it adds negligible additional load because all you're doing is randomly sampling packets. So that's an unmeasurable additional load, and those packets are then just getting kicked out as UDP databases. It doesn't really consume any resources.
When the sampling rate is low, then I think the load is high.
Yeah, you can always choose to break it. If you were to sample 1 in 1, it would break. But you don't need to sample 1 in 1 for these kinds of use cases. And if you wanted 1 in 1, you're better off using OpenFlow to tap the flow. So that's not a good use case for sFlow.
One quick question for you. Have you seen a use case where there is a hierarchical sampling where you have kind of sample a subset and then you at the next layer sample a new subset? Have you seen a use case like that?
Well, sFlow certainly doesn't support that. And so we haven't seen use cases for it. I think it just adds an incredible amount of complexity for what I don't see as a lot of gain, because as soon as you highly tune the agents to perform a particular measurement, those measurements are then much less useful for other purposes. So the idea with sFlow is that it is software-defined measurement. You do a very simple thing in all the agents, and then all the intelligence resides in how you analyze that data. So if I want to break out my flows in different ways and have different perspectives on the data, I do that at the receiving end, not at the sending end, because there's only so many, there's a limited number of resources in the switches to make measurements. And so if each application commits those resources, then you have a finite number of applications you can run. Whereas if you do the analysis centrally, you can have an infinite number of ways of looking at the data. And all it does is, just consumes commodity compute resources, and they're far more abundant than resources on the switches. You had a question?
Yeah, what about using sFlow versus, say, SNMP, and just some of the differences?
Yeah, well, SNMP is used in a polling configuration, and so polling is just a lot less scalable. Essentially, you could think about sFlow as scale-out polling. So rather than have a central box that has to poll, 30,000 switches, you have 30,000 switches polling themselves and sending the metrics. So as you add more switches, you add more polling capacity, and it scales for as big as network as you want to build. Whereas if you're polling with SNMP, you end up with banks of pollers. You don't have, it's hard to assemble sort of a centralized view, and there's only so fast that you can poll. We found a lot of switches, if you poll them aggressively, it buries their CPUs. And the last thing you want a performance management tool to do is be your performance problem. You want higher frequency counters. So with sFlow, a typical setting would be maybe to export all the interface counters every 20 seconds or so. Whereas with polling, you're lucky to get every 5 minutes, typically. Yeah, the other thing is, a lot of counters that sFlow is exporting, particularly, like on the hosts, a lot of people don't want to run SNMP agents on their servers. It's just very efficient to just grab a bunch of counters out of /proc and send them out. Again, it's negligible load, whereas if you're running a protocol stack like SNMP, it consumes far more resources. It also increases your attack profile because you're having to listen to a protocol. And you could actually be DDoSed with SNMP, or maybe there's a buffer overrun attack. Whereas sFlow doesn't listen. It's purely a send protocol. And so it can't be compromised by an attack.
Peter, I have two questions. One question is like you mentioned about sFlow application layer module. Is there some kind of a lib like you can build with our, even like other than Apache, we can build with our, I have applications where I'm running like a custom protocol and I have like millions of clients connecting. Is there some way I can link this with the sFlow thing and I can get metrics out of it?
Yes. The idea with sFlow is that there are certain just very widely used protocols like HTTP and Memcache, and we're hoping to work with some storage vendors, so like NFS and iSCSI, that you'd want really standard metrics. And there's a bunch of in-house applications or custom applications where it's really just not worth the bother. And so what we've defined with PayPal actually, because they have a bunch of in-house applications, is really kind of a standard representation of a networked application. So key things, like the idea of an operation, a response time, a set of status codes. And so what you can do is you can, if you've got your application written in Python or PHP or something, you can basically just send a JSON encoded sFlow structure down to the host sFlow agent on the box, and it'll handle all the sFlow protocol for you and send it out as something that's very much like the HTTP sFlow, but it's your own sort of operation namespace.
Okay.
And then you can get all the same sort of analytics.
And second thing, you showed some pretty plots with the tenancy, right? And you mentioned about Hadoop clusters.
Yes.
That you can look into the network now and you can see where the traffic is going and you can make recommendations what should be the ideal topology of the machines where they should be deployed. But is it currently being used during the runtime with Hadoop clusters somewhere? Like people are using this somewhere, or do you think it can be done? Or
sure. I mean, the thing with sFlow is that really it's not an as needed kind of measurement. It's an always on. So I mean, production Hadoop clusters, the top of rack switches are running sFlow. You're getting continuous visibility from every single switch port, and you get to build the full traffic matrix. Every host to every other host. And so that's the kind of data you want for that kind of optimization. It's not sort of link or device oriented. You can take all that data and put it together, deduplicate it, because you're monitoring, traffic might pass through 5, 10 links. But because you're getting data from all those links, you can put it together and get an end-to-end traffic matrix, which you can then use to drive sort of dynamic topology, sort of planning and optimization routines.
But the Hadoop topology is for the particular job, right? And once it is deployed, you can change the topology only after the job is done, right?
Yeah, so I think,
in between, right?
Well, I think the thing with Hadoop is that what you'd want to do is make the Hadoop job scheduler even smarter about the network resources. So if it could see what parts of the network were utilized, it's got a lot of choice in where it decides to hand off a job. And so it would be the controller in that environment. It's harder if you just have an external controller just reacting to what happened. It's the same sort of thing with network virtualization. What you really want is the compute manager that's placing virtual machines to be network aware, so it places those virtual machines sensibly with respect to the network. If it messes up its placement, you're much more limited in how you can engineer the network to respond to that. In fact, the most powerful lever you have to engineer traffic in the network is the placement of the workloads. The old school idea of network topology planning was you take the traffic matrix as an invariant and you design a topology to suit the traffic matrix. Well, with cloud computing, the traffic matrix isn't an invariant, it's a variable too. And that's where I think if you broaden the scope of the system, you don't maintain the traditional silos of networking, compute, and storage, but you move, one of the other things that Hadoop does that makes it perform well is it moves compute to storage rather than storage to compute. And so it's the same sort of thing when you're orchestrating OpenStack. You really don't want sort of Swift to be separate. You really want there to be an overall orchestrator that's saying, okay, I know where the storage is, I know what network resources are available, and I know what compute resources are available, and that's the best place to put that guy because that's the storage he wants, that's who he's going to talk to. And then you can do dramatically better in terms of utilization of resources. If all you're doing is being stuck with a plan that says, okay, wire up these tenants, what can we really do? There's very few degrees of freedom left.
So you can really result. It can really result in having to reduce the amount of physical network switches you have to deploy.
Yeah, well, old school network topology design is minimize the hop count.
Right.
That's locality. So you want to put people as close as you can put them, and still meet the constraints of like high availability. So Hadoop does that. Says, okay, I'll replicate within the rack, and then I'll throw one off rack to make sure that if the rack fails, I still have access to the data. So it's that kind of thing. You say, okay, it's a constrained optimization problem, but wherever possible, local's better.
Can you explain a little more about how random sampling you're able to sort of map out the physical network topology in the network virtualization example? So would it take a lot of time for you to sort of map out how the physical topology is getting used? Because it's purely random sampling.
Well, knowledge of the physical topology, if you're using OpenFlow, you have absolute knowledge because it's in your database. So you don't need to discover it with sFlow, but actually you can do a pretty good job of topology discovery with sFlow, and then it also gives you the analytics. So the way you discover it is that, I kind of skipped over this in the introduction to sFlow, but when you take a sample, it's actually used to probe the forwarding state of the switch. And so you don't get just the packet header, but you get the fib that's associated with that forwarding decision. So if it was switched, you'll get the sort of ingress, egress, sort of VLANs and priorities and ports. If it was routed, you'd get the source and destination, subnets, next hop router. If you were using BGP, you'd get the AS path and communities and so on. And so you get really rich view of the forwarding state associated with each sample packet. And so if you take, if you decode out all the headers in the packet itself and you combine it with the fib data, you can imagine each sample is just sort of a little a dot in a picture. And you put all the dots together and you have a little picture. And you can sort of basically string these little pathlets. And you get enough of them and you have a real-time view of the topology. And as soon as anybody comes on your network, you know exactly where they are, what communication paths they're using in pretty much real time. And then you get the volumetric data. So how much traffic are they generating? Are they going across links that are seeing discards? You can actually look into tunnels very easily because if you think about it, both the outer layers of a tunnel and the tenant information are just laid out for you in the packet header. So you just deeply decode through the packet, and you can see the tenant's IP address space. You can see the VNIs from the headers, and so you can tie the virtual topology to the physical topology. So that's a really interesting use case as well. Troubleshooting virtual networks is somewhat of a nightmare. If I have a tenant complaining that performance between two of their virtual machines is bad, what are you going to do? Whereas with sFlow monitoring, it's really easy. Just drop in a filter, say I'm interested in these two tenants talking, and then you peel out the outer layers, and you see the physical path that it's taking. You correlate it with the interface counters. You can see if there are any discards or performance problems on the links connecting those machines. And you can also look at the hypervisor loads and so on, and tie it all together.
I'm still struggling with one question. When you say real time, what do you mean by that? Because if you want to go real time, you need a lot more samples to come to the server to correlate, right? So that's what, like when you say real time, like if you're only sampling 1 in a million or really at slow rate, you won't get real time data.
Well,
on the other side,
how is the sample?
Well, real time is a relative term. To a control engineer, real time is fast enough to implement feedback control. So real time for something with a time constant of a minute is around a minute. Real time for something that, like a packet queuing discipline on a switch port, is nanoseconds. And really what you see when you're looking at the data center are a bunch of nested control loops like Russian dolls. So you have the queuing discipline on the ports, and then you might have the ECMP load balancing and detection of failed links and routing protocols. And then you have, stepping back, the timescales that we're really looking around here with SDN, which I see as sort of the order of seconds. And so when I'm talking about real time here, I'm talking about these sort of bandwidth management problems where you want to, say, steer large flows. And there, if you can respond within a few seconds, these are flows that are lasting 10 seconds plus. So if I've acted on it within 2 seconds, I've steered 80% of the bandwidth that that flow carried. And so that's real time with respect to that task. And a sampling rate that gets you there is about 1 in 1,000 for a gigabit port. And it scales pretty much linearly. So if you're going to a 10 gig port, it'd be 1 in 10,000. If you go to a 100 gig port, it'd be 1 in 100,000. And that would get you the ability to find anything that consumes 10% of the bandwidth of that link within about a second. And really, it's a relative term. I mean, I don't care to micromanage bandwidth. If you're not using 10% of the bandwidth, why do I care? Why am I going to burn OpenFlow rules on something that's going to have no impact? I'm going to steer the top talkers. And so really that's the idea here. And the other thing is that sFlow, one of the reasons it scales is, as I kind of touched on earlier, is that most links are idle most of the time. There's just, there's hotspots that are just kind of like moving around randomly. And if you set a constant sampling rate, so every 10 gig port on your network is set at, say, 1 in 10,000, then most of them are sending you very little data. And so and cranking up the sampling rate there is really just cranking up the noise for your measurement system. You really want to allocate, you want a high signal to noise ratio, and so sFlow just very naturally gives that to you. If somebody is talking, they generate samples, you very quickly resolve what they're doing, and you can act on it, and you're not distracted by all the guys who are doing nothing. Whereas flow-based measurement technology is, a flow of 1 packet's a flow. It counts the same as a flow of a megabit per second or 100 megabits per second. Whereas sFlow allocates, quite a lot of resource to monitoring the very high capacity flow, which for a traffic engineering point of view is the one you care about. And it gives you a completely impartial and correct view of the tail. So, if you have a million, say, 100 megabytes per second, whether it's all individual flows of one packet, one flow that's responsible for all of that, you'll correctly resolve the total bandwidth consumed, and you'll know whatever common characteristics there are that you could use to steer that traffic. So it's not that you have no visibility into the tail, but you're sort of pooling that tail into sort of mega flows that characterize whatever common features there might be.
Do you have any capability to associate a particular flow to an application?
Okay. Yeah, I mean, again, the idea is that each thing reports its own state. So if you have, say, your Apache web server reporting sFlow, it's going to report the TCP socket that it received the request on. And so now I know.
Does sFlow limit itself to just the networking parameters, or is it more like how many threads this particular service is using?
Yes, so also some of the counters that we reported by Apache are the scoreboard data, so you know how many active and idle and a maximum number of threads that are available. And those counters then would let you find, like attacks like slow wars or something where you're just trying to suck up resources.
So your analytics as such has capability to scale across multiple different layers in the stack and coding.
Yeah, that was that slide which was showing the entity relationship diagram, showing how you can join this data dynamically.
Most of them were focused on the network aspects of it, but I was just wondering if there is other perspectives.
Yeah, well, the basic model is sort of communicating entities, whether it's at layer 2 or 7. So the application entity for HTTP will be like URLs and things, which tells you what service you're accessing and what operations you're doing. So I'll move on to the sort of demo part. So I don't know how many of you have downloaded the sort of prerequisites here, but I'll be kind of walking it through so you can do this later. I'll put the slides out and you can try it later if you want. But basically, you need to have downloaded sFlow RT, and it's a Java application. And then there's a PCAP file that's distributed with sFlow RT. And this diagram kind of shows you the little test network that generated that data. So it's a Zen server tool. There's also a Hyper-V server. There's a bunch of VMs running on those servers. There's also a physical switch. And the vSwitches are instrumented, so they're giving packet samples and counters. And there's a bunch of, as I said, a bunch of VMs that have host sFlow installed on them. And then you have applications like HTTP, Memcache. There's a PHP application and Java. And those metrics are being exported as well. And so to configure it to use that PCAP, you just change the start script to read the PCAP file. And then when you start sFlow RT, you'll see that confirmed by that second line there. It's saying that it's reading the PCAP file rather than listening on an IDP port for sFlow.
Can you go back to how to load the PCAP file?
Sorry?
How do you use the PCAP file? What do I have to do?
You have to edit the start.sh script in the sFlow RT home directory. Yes, so back here. So it's basically passing it as a JVM opt. So currently the default string is empty, and you just put in that one -D sFlow.file equals, and then it's in the extras subdirectory in its demo.pcap. And then if you were, deploying this in Anger, you would also probably give various JVM options to limit the amount of memory that sFlow RT can use, and so on. And you'll also find other things in the extras directory. There's actually an init script if you want to run it as a daemon on Linux. Has everybody got that? There's also, if you look at the README in extras, it gives you that command line. That line that you have to edit. Yeah. Okay. So I don't know how familiar everybody is with sort of RESTful APIs, but the idea is to use HTTP semantics as your application model. And so with sFlow RT, one of the key things is this concept of a metric. And a metric is really a gauge, a number that you can trend or threshold on. With any kind of controller, what you want are numbers that you can react to. And so you want to try and turn everything into a metric. And then there's this vector of metrics that you're using to characterize the state of your system. And so the way that the URL is constructed is that you have the function that you want to do. In this case, it's metric. And then there's a scope that you're going to use to scope the query. And it's the agents, which is sFlow terminology for the things that are sending sFlow. Each entity sending sFlow is an agent, and it has an agent identifier, which is an IP address. And then you have the particular metric that you want to retrieve. And within each entity, there are various data sources. So if you're looking at a switch, as in this case, the data source would be the port that's reporting the IFing TETS value. And so it would be, that would be IF index 1, and you're getting the in octets, and the type, you're saying I want a JSON response. And then more fully here, you can play around with each of those fields. You can change the scope. You can have a whole list of agents that you're interested in, so you can query across a bunch of them. There's a special token, all caps, all, which means every agent in the network. And then you can provide various kinds of roll-up operations with these sort of column sort of prefixes to the metrics. So if I was interested in the maximum interface utilization across all ports in my network, I would just put max in front of IF utilization, and then I would find the busiest port in the network. And I can do other things like variance, average, standard deviations, medians. You can get your quartiles, or interquartile range, which is the spread between the third and second quartile, or just any, which means I don't care which one. Just give me an exemplar of that metric. And then there's also filtering that you can do, so you can scope, you can retrieve a metric scoped by filters on other metrics. So in this case, we're filtering on the operating system name. And this is an example of sort of like joining data between different layers. So you can say, okay, I'm only interested in systems that are running Linux or Windows and would have 2 CPUs. And the key concept here when looking at the flow metrics or any kind of samples that sFlow RT is looking at is that you use, when you define a flow, you're essentially defining a metric. And so the elements of the flow are what metric am I going to be creating here? And so that's the name. And then there's a number of keys. So, this example here is just, I'm interested in TCP connections. So I want to see the IP source, IP destination, TCP source port, TCP destination port. And that's going to be my flow key that I'm going to be building. And then I'm interested in a value that say maybe the bytes. So and what it'll do by default is compute the rate of bytes. So it'll be bytes per second is the metric you're creating. Other kinds of ways you can manipulate that operation is count. So you could say I'm interested in counting the number of IP sources against, say, destinations. So I might set up a flow that's IP destination and count of IP source, which is kind of useful if you're looking at DDoS attacks. You can distinguish between just a big flow or a flood from lots and lots of attackers. And then you can do operations on addresses. So like masking, you could say, okay, apply a /24 mask to the IP address and just roll up and report the flow with that granularity. And then the filters, again, you can filter on any of the fields in the flow that have been decoded. So I could be filtering on ports and reporting other fields and so on. And what you end up with is a metric that represents the largest flow for that metric seen by that data source. And it'll actually keep a top N in there, but the one that gets reported as the metric is the top one. And then you have the sort of HTTP operations to sort of manipulate the state of the tool. So creating new resources, you use HTTP puts or posts. In this case, to create a new flow, we're going to post to compare it with the name, or we do a put, and then the name exists within the URL, and use providing parameters. And then you can read back the definition that you just created using an HTTP GET. You can rewrite the flow definition by using a put again, or delete it using HTTP delete. Or you can actually do a post of an empty value. It does the same thing. And there's a list operation. So again, if you access the parent, you'll get all the children, which lets you see what flows have been defined. This is when we go through some actual examples. I'll drop out here. Okay, so this first example, it's kind of at the bottom here. Let's see if I can. So this is just basically, I'll be walking through all the basic operations to give you an idea. Getting the version of the software, not terribly exciting, but it's useful if you have dependencies on the particular version. It's also a pretty good way to do a keep alive. It's a very cheap operation. You could essentially ping the server and see what's up. The next one is you want to make sure that your server is not overloaded, and this just retrieves a bunch of statistics with respect to the Java virtual machine. Again, not terribly exciting. The next one is pretty useful. This is sort of a listing operation. I want to see what agents are reporting data. So these are all the switches and hosts that are sending me sFlow data. If I had DNS here, it would also be telling me the host names or DNS names. The other thing that's really useful is to see what metrics are we seeing, because depending on what devices are out there, they'll be telling me different things. So in this case, there's just a bunch of different metrics, and it's telling me the last time I heard that metric. So I can see whether these metrics are current or whether they were heard ages ago. And you can see things like reads and writes from the host sFlow agents. These are sort of operating system I/O reads and writes. You get things like I/O time, which is useful to see if you're this is slow, and CPU utilization. It's also giving you, if you're running on a hypervisor, which one of these agents, some of these agents are, it'll also report on all the virtual machines that are running on the hypervisor. It basically exports all the libvirt metrics, so you get to see all the virtual machines, their CPU loads, UUIDs, and so on. And for all the network devices, as I said, all the interface counters. The next one is just sort of showing you that you can sort of scope these metrics. So now if I want to see what metrics a particular agent is reporting, here I'm looking at a particular switch, and I can see which data sources and values are being exported. And I can see what they are. So I can see the IF type for IF index 6 is it's an Ethernet port. And I can see its other counters. And this is an example where you're looking across all the agents. I'm saying, okay, I want to see what the busiest server is. And so it's saying, okay, here the metric N is the interesting one. It's saying, okay, there were 14 servers, and I looked at all of them, and the highest value is 0.62, which is pretty low. The last time that value was updated, I've got the time since the epoch, and which data source on that agent reported it. So that's kind of pretty useful to see where the hotspot is. In this case, you can have a bunch of different metrics you're interested in. Maybe you want more than one, and so they come back as an ordered list of metrics. And in this case, let's see, we just seems like a replica. Here we're scoping it by agents, so we can see. I'm just interested in which of these two agents is busiest. And what's really useful is when you combine these with some of the filters, you might want to, you might have dozens of different clusters running in your data center, and you're monitoring all of them here. And so you might put a filter in and say, okay, I've got some naming convention for host names. And if the host name starts HTTP, I know it's in my web pool, or it starts web. So you just do a filter on host name equals web star, and then you will just get an aggregate statistic for the web servers. And then the dump is really useful. You say, well, I'm not interested in just in the maximum value. I'm doing a load balancing decision. I'm really interested in seeing the spread of loads. I want to know everybody's load. And so you get a list of everybody in the pool and their loads. And this is an example where we're doing the filtering here. So we say, okay, I'm interested in all the Linux servers where the host name is prefixed Z server. So those are the 3 Z servers in the server pool. And we can see which one's busiest. And this is an example where you're wanting to look at some of these statistical operations. So I want to see what's the spread of loads across my server pool. It's a good way to see how well balanced I am behind my load balancer. And so here we see the max, min, and standard deviation. And for the guide, it's the maximum. You identify the particular server and the minimum and so on. Okay, so the next couple of examples are looking at flow definitions. And so this is where you're actually defining your own metrics. SFlow RT comes pre-populated with anything that's sending counters because they just become a metric. But with flows, there's an infinite number of ways in which you could aggregate, hundreds of different keys that you could extract from the header. And so you have to explicitly decide what kinds of flows you're interested in. And so flow keys tells you all the fields that SFlow RT is currently able to extract from the data it's seeing in the network. And so you can see some really interesting ones here. Some of them are application layer ones being, for instance, the URI file is being reported by the Apache web servers, and it's telling me, the file name from the URLs as it samples those. Other ones are reported from the switches. Other ones here are like memcache servers are being instrumented. And so you have things like the keys, the number of keys in the operations, protocol versions, and so on. And then some of them are actually done by this dynamic join. So some things like OS name, source, and destination, it's actually taking the SFlow data from the switches, and it's looking at the MAC address, and it's taking the SFlow data from the servers, which are reporting things like host name and utilization of the server, and the MAC address of the NIC card, and it's doing the join, and so it's able to report the flow then by hosts. So I can do traffic from a server, for instance, by just getting the UID of the server, the host name of the server. And that's really an interesting problem to solve if you're looking at the network, because you might have a server with 100 IP addresses and many NIC cards. If I want to see all the I/O that server is doing, no matter what card it goes out on, no matter what IP address it goes out on, this dynamic join lets you, in one query, say, okay, tell me everything to do with that server. What's its total network I/O? Where is it going? What's it doing? So given those flow keys, then you can start defining flows. And this first one is kind of interesting. The stack token represents the sort of decoded stack. If you're familiar with Wireshark, it's a similar kind of notion. You get a dotted decimal sort of set of names that tells you the layering of your protocols. So let's sort of push that flow definition out there and say, okay, I'm going to define a new metric called stack, and it's going to be looking at the top layering with respect to frames per second. And then now I can retrieve that metric since I've defined it. And here we can see that the top flow is TCP over Ethernet, over IP over Ethernet, and it's 970 frames per second. The next example is I'm interested in defining a flow that says IP source and destination, and I want to look at bits per second, or bytes per second. And so I have defined that flow. Now I just retrieve the metric. It now exists within the set of metrics, and you could do all those operations that we were doing with any metric with the flows. And so now here I can see, okay, there are 16 data sources that are exporting flows to me, and the maximum flow is this particular pair of IP addresses, 10.0.52 to 10.0.54. So I define the template in terms of the flow names, and then what I get back are the specific instances and their volumes. This next one is showing you how you apply functions, and so we're going to mask the IP addresses by /24, and we've defined it, and so now we can retrieve that metric. And we can see that it's all in one /24 network. There's no other ones we've seen. This next one is showing you sort of the application layer. It's really interesting if you have deep URLs. You often, the top level token represents the application, and so you want to just roll it up and you say, okay, I'm just going to split the URL on forward slashes, and I want the first token, and I'm going to then look at requests per second as my metric. And then I just, again, I retrieve it, and I can see requests per second against each of my top level applications running on the web core. This next one is really interesting. Normally, you have understanding how your address space is allocated is very useful for classifying traffic. And so what you can do is you can push in named lists of CIDRs and use them to classify traffic. So here we're just saying, okay, I've got a default name for traffic, which is external, and so it's the default /0. And then my internal traffic, I'm just using all private address spaces. And so I'm just defining those two tokens. But you could do other useful things. Suppose you had knowledge of 1 million, say, IP addresses that were blacklisted because you know that they're compromised in the botnet or something. You can push those in and classify them as the token of the botnet. So I don't need to enumerate them every time. And so you just push that definition up. And here we can just sort of read it back, and we can see that that JSON object now is known to the system. And what it actually does is, if you were to look at the flow keys, you now have new keys available, things like source group and destination group, which are pull out these tokens. And so we'll define a new flow that's source group to destination group, and we want bytes per second. And now we've defined that, so we can read it back, and we can see, well, it's all internal traffic. I'm not seeing any external flows right now. And this kind of classification you'll see later using a DDoS attack. It's an external attacker, so you can ignore all your internal traffic by just saying, okay, I'm interested in my top flows from external sources to internal destinations with various filters. And that way I can craft very specific metrics that I'm using to drive that control. This one is pretty interesting. Suppose you want to trace how packets are flowing. You have, I mentioned earlier the idea that suppose you have a problem with a tenant in your network and you want to trace their traffic across the physical infrastructure. Well, this is sort of a similar example. I don't actually have any tunnel traffic in this trace, but I'm saying, okay, I'm interested in looking at traffic between a particular IP source, 10.0.150, to a particular destination, 10.0.151. Suppose I have some kind of performance problem, and I want to see how is that traffic traversing my network. So what I want to see are the input, ingress, and egress IF index on each switch as it traverses my fabric. And so that's what this flow will do for you. So we push that in, and now instead of looking at like the top one, we actually want to enumerate all of them because we want to see the full path that it's taking. So we're going to use dump instead of metric, and here we have it. Every agent is reported, and the ingress-egress pair of ports that those packets are taking across each switch is revealed there. And then you can make a subsequent query using that data and say, okay, I can now enumerate all the indexes that I'm interested in, the interfaces, data sources I'm interested in, and look to see if there are any discards and errors on those links and what the link utilizations are. And so within an instant here, I can pull back an analysis that tells me, all the status of all the resources that flow depends on. And I can also target, the two endpoints. I can say, okay, is the server busy? Is the client busy? How are the applications looking? And I can, through a set of queries, I can put all that data together and get a complete picture of the state. And so, we defined a bunch of flows here, and you can see, I can enumerate them all, and you can see the ones we've defined here. And they're all running in parallel. And that's one of the nice things about doing this centrally, is that I can have as many flow definitions as I want, and I can run them all in parallel. Whereas if you're trying to do this on each of the switches, each of them has a limited number of flows that they can run concurrently, whereas I'm limited only by the amount of CPUs and memory I'm prepared to put on this central server. And I can keep adding new fields just by adding more decodes to the central collector. Whereas if you're relying on hardware analysis, if it doesn't know how to decode a field, you're out of luck. You have to wait for a hardware spin. And this next one shows I can retrieve the definition for a specific flow, and could delete it and so on. This next example is showing how we're going to define a threshold. So, it's one thing to have all these metrics. I don't want to just sit here polling all the time. It's useful to be able to define thresholds, and this is done by accessing the threshold operation, and you define a named threshold. In this case, we're going to call it source destination because it's going to be on the source destination metric. And we're saying, okay, I'm interested in seeing any flows where I see more than, I think it's a megabyte per second. And so I push that threshold definition in there. And I can read it back. There's the definition. And then whenever that threshold trips, it generates events. And we can see now the event log that's being generated. And each event tells me the agent and data source and metric that tripped the threshold. And then if I'm interested in the particular values, for instance, to enumerate the flows that are being seen on that entity, I can make a metric request using this data and retrieve the details. And I can also ask for a particular number of events and retrieve those. And this is particularly interesting because you're still sort of polling here. And what you want to really be sort of asynchronously driven. So the instant the threshold trips, you want to be notified. You don't want to have to wait until the next polling interval. And the way to do that in HTTP is what's called long tail polling. And there's an example in the, let's come back to the presentation here.
Peter, I have a quick question.
Yes.
I just want to ask, is there a specific characteristic of the central system? Is there a characteristic that you have for the data, where you collect all the data, all the samples from the agents? Or is it can be any type of database or?
Well, in this case, I mean, that's the thing with sFlow, is that there really is no standard for sFlow analysis. The standard exists, as soon as the data hits the wire, sFlow's done. It's defining metrics. And so really there's an incredible variety of sFlow analyzers. So, if people are familiar with Graphite, you can use Graphite as an sFlow analyzer to report metrics. You can use Ganglia, also natively understands sFlow. sFlow RT builds an in-memory database because it's interested in very fast response times. It has no history, but you could poll these metrics and put them into Graphite. And there are other products like our Traffic Sentinel product that builds a database that you can then query for longer-term trends and so on. So there's no such, there's an infinite variety of things you could do. Yes?
Can you identify applications like YouTube, Skype, using this data?
This focus is really on the data center end. So if you're Google and you're providing YouTube, and you're running sFlow on your YouTube servers, then they would be reporting sFlow application transaction samples, which would tell you the ports involved in each YouTube session. And so you then correlate that data with data from the switches, and you can classify the traffic.
is like I have a YouTube traffic packet capture going between my network.
Yes.
So can I identify that it's YouTube using this?
Well, you can tell, what you would probably see is that it's a TCP connection. If you know the CIDR that is the Google data center running YouTube, then you could define that as a group and filter on the IP addresses. But if it's your application, then you know for sure, because the application is declaring itself as being responsible as the service sitting on that port. And so the if it's a resource you're actually managing, then you know for sure. If you're at the other end, you're kind of guessing. Unless you run sFlow agents in your web browser or something, then it could know too. Yeah.
So if I want to write an analyzer for myself, are there any libraries like open source that I can just use to read sFlow packets?
Yeah, a good starting point is sFlow tool. It's an open source sFlow decoder, and I think most sFlow analyzers have been built using that as the front end. Doesn't get you, there's a lot you do beyond that. And so it really depends what you want to do. If all you want to do is pull out the load average, then that's really easy to do. It's just a number that you decode out, and sFlow tool will pretty print it. And so that's a very easy task. If you want to do flow analysis, then you need to do a decoder to decode the raw packet headers. And you also need to do scaling of the sample data and so on. And so it can get more involved. It depends. But the very first thing of just decoding packets is pretty simple, and that sFlow tool is a good starting point.
So do you have any?
Are most load balancers already aware of layer 4 and layer 7 information? Can they use that information to do the analysis of the packets?
Well, they're aware of it, but an external observer isn't necessarily. And so the load balancer isn't the only thing in your data center. If I want to orchestrate everything around the load balancer, then I want to have the load balancer export sFlow and tell me about its state, so that I can now take the data from all the load balancers, because I might have hundreds of them in my data center connecting all my different virtualized scale-out clusters, and I want to be able to correlate performance tier to tier, correlate with metrics that the load balancer doesn't see, like whether the servers are swapping. You could have some really clever denial of service attack in which they're doing resource exhaustion attacks, and you see that all the CPUs on all the servers are spinning like crazy. The load balancer can't see that. It's just seeing, oh, I'm giving an equal number of connections to each server, I'm fine. Whereas if you're also monitoring the servers, you can correlate the two. And if you're monitoring the network, you can say, okay, the performance is bad because some other traffic is blasting across the network, and I'm seeing discards on an important link. So it's that ability to put it all together and then orchestrate solutions that no point device can fully appreciate.
Do you use UDP to collect all this inputs?
Yes.
So
that.
These packets in the hardware switch, is it sent to the control panel? The sFlow packet?
So I didn't hear the question.
Speak up.
How are these sFlow packets sent? Are they sent using the regular switch data path, or is there a separate control path?
It's not defined by the standard, so it's really up to the switch vendor. I mean, it's basically just a UDP packet with a destination IP address. And so if you're sort of sending it on the management network, it goes in the management network. If you send it in band, it goes in band. If you want to send it through an IPsec tunnel, it goes through the IPsec tunnel. It's a provisioning exercise that's sort of beyond the scope of sFlow. By itself, it has no security, no encryption. It's just very simple UDP XDR encoded payload.
So essentially, sFlow provides protocol to exchange the monitoring information and how you use that information is all, it's up to the agents or the controller.
Yeah, I mean, it doesn't even define the configuration protocol, except, I mean, it has an SNMP node that you use to configure it, but it's really about defining standard sets of metrics and their representation on the wire. What protocol done? Yeah, once it hits the wire, done. And so it's the semantics of the measurements, precisely what sets of measurements. And that's one thing that distinguishes it from a lot of other things. There's a tremendous value in having blocks of data. One number by itself is kind of useful, but if I have a block of like 10 counters and I know they're always going to be there, then I can compute geometrically more ratios and combinations, and I can sum them and divide them. And so that data is much more useful than if I just have ad hoc sets of things. And so, I see that as really the value of sFlow is in being very prescriptive about the particular measurements that everybody must make. And you get tremendous interoperability in them because everybody sending sFlow is going to send you exactly the same data, and you get a complete end-to-end view. Whereas that's one of the issues with things like IPFix, is really there's no such thing as a standard metric in IPFix. It's really just a descriptive protocol. It's whatever you want to export, and here's some tags. And so I have no guarantee that I can get the same data from every device in my network. Each guy just exports whatever they happen to have.
Well, actually, there was an interesting comment made about hierarchical accumulation of monitoring data. For example, if you have a cluster of 700,000